Question? Sorry? Oh no, I'm working out, but I'm not working out. I will be here on Thursday, so in as much as I sympathize with the organizers, and I think that they really have a very valid points, they've raised very valid points, I also feel that my job is to be here, so I will be here on Thursday. Any other questions? Perhaps even more important, next Thursday we'll have our first midterm exam. Okay? Yeah, everybody's excited. So I already put an announcement on the BSpace page, which, by the way, you should check BSpace site because there are all kinds of there's all kinds of interesting stuff in there and useful information also. So homework solutions, something I have already told you about. But also there will be some information about the exam. This week I'm going to post a mock midterm so that you will have a chance to practice for the midterm. And we'll have a review lecture next Tuesday, a week from today. And the exam is on Thursday exactly during the class hour, 1 hour 20 minutes more precisely. So we'll start at 3:40 and finish at 5. Because this room is not big enough, because everybody will be packed, so I have requested another room. So we'll have to separate into two groups. I will post information about this, and I will tell you about this, everything about this on Thursday or next Tuesday. Okay? And now I go back to what we talked about last week, which is limits. I just want to say a few words about limits, and then we will move on to the next subject, which is partial derivatives. So about the limits. Too many late arrivals today. I'm going to charge a late arrival tax if this continues. So let's just quiet a little bit because it will be good for everybody if we are more focused. Okay? So limits. I illustrated limits by way of an example, and I looked at a particular function in two variables, namely x squared divided by x squared plus y squared near xy equals 0, 0. And the reason is that at this point the denominator becomes equal to 0, and so this expression becomes problematic. It may or may not have a limit. If we did not have that, if for example we looked at this function near a point xy equals 1, 0 or 1, 1, a point where the denominator is not equal to 0, that would be an easy question to handle. But precisely when the denominator becomes equal to 0, we have to be careful and we have to analyze it more precisely. And so in this particular case, I explained that this function doesn't have a limit. This function does not have a limit at this point. And I explained this. I explained the reason. The reason is that we could find, the reason I gave was that I showed two different paths. Two different paths on the xy plane, which approach 0. One was the path when x is equal to 0, so it's a green arrow, and the other one was the path when y is equal to 0, and that's a red arrow. And we have seen that along the first path, when x is equal to 0, when we look at this function on this path, very close to 0, but not quite equal to 0, what we get is a 0 divided by 0 plus y squared. But as I said, we really look at it not at this point, but just near this point. So near this point, y is not 0. So this is not 0 near the point. Because it's near the point, we can actually evaluate this. And we see that for all values of y near this point, this is actually just plain 0 because it divides 0 by something non-zero. And so this means that along this path, there is a limit, and it is equal to 0. On the other hand, if we look at this path, we get x squared divided by x squared plus 0. And again, we will assume that x is very close to 0, but not quite 0 yet. So this is actually a non-zero expression, and therefore we can cancel them out. So this again is non-zero. And this actually gives us 1. So that means that along this path, again, there is a limit along this path. There exists a limit. There is a limit along this path, namely 1. So we have found two paths along which we achieve a different limit. We attain a different limit. That means that the function itself does not have a limit. You see, it does not have a limit. Because to say that the function has a limit, if along any path approaching the point, the limit exists, and all of them are the same. In this particular case, clearly they're not the same because there are two paths, at least two paths, along which the limits are different. So how can it be that a function has different limits along different paths? In other words, what is the meaning of this? What is the geometric representation of this? Well, to explain that, we can already see an analog of this phenomenon for functions in one variable, which I explained last time. In the case of one variable, we look at the graph of a function as a geometric representation, and we can have the following situation where the graph is discontinuous. Oh, grab the same color, yellow. So graph is discontinuous, for example, like this. So there's some point x0, and if you approach from the left, you're going to end up at this point, and this value, and if you approach from the right, you end up at this value. So that means the function does not have a limit at this point, okay? Because along different paths you get different limits. They're both finite. So in some sense, you can argue that it's a more benign situation than, let's say, a situation of a hyperbola, or actually goes to infinity. Here, by the way, on the right it goes to plus infinity, on the left goes to minus infinity. So in some sense it's even worse than just going to infinity. It actually goes to two different infinities in some sense, right? But first of all, if it goes to infinity along any path, we already say it doesn't have a limit. But even if it's finite, this situation, which is in some sense more benign, it still doesn't have a limit. It has a limit from the left, it has a limit from the right. In the case of one variable, there are only two possible paths which converge to this point. Well, you can go sort of with different speed, different velocity, but it doesn't matter. I mean, geometrically it's the same path. Either this one or this one, only two. And already that creates trouble. In the case of functions in two variable, there are many more paths. I have drawn two paths here. Here's one, here's another, but you have many more, right? You also have a path like this. Finally, a path doesn't have to be a straight line. It could be a spiral, So there are many different paths, and that's the difference between two variables and one variable. to say that the function has a limit for a function to variables is a very strong statement. It's a statement that along any of those paths you're going to achieve the same limit. So this actually shows that in a way it's much easier to disprove something here, to show that the function does not have a limit, than to show that the function does have a limit. Indeed, to show that it doesn't have a limit, it's sufficient to just exhibit two different paths along which you have different limits. And usually, it's pretty clear which ones you should take. For example, in this case, you just look at x equals 0, y equals 0. Sometimes you might need to look at a linear path, like this one, where x is equal to y. Again, to convince yourself that indeed the function doesn't have a limit. But to prove that actually the function does have a limit is much more difficult, because it wouldn't be enough, for example, to say that the limit along this path and along this path is the same. You would also need to show that the limit along this path is the same and along infinitely many other paths, right? So to show that it has a limit is more difficult, and this is not a very efficient way to show it. It is very efficient, this way of argument is very efficient to show that it does not have a limit. Because then it's enough to show just two, for which the limits are different. But to show that it has a limit, it wouldn't be enough to show that along two paths you get the same answer. You have to show that the same goes for all paths. Okay? So for practical purposes, what you need to know is the argument showing that it doesn't exist. You need to know this way of argument. When the limit doesn't exist, you should be able to demonstrate that there exist two paths along which the limits are different. Okay? Yes?
So for longer paths, you do a spiral.
Yes.
Does it really matter if it's a spiral, or does it just matter? It seems to me that it doesn't matter like instantaneously, right?
The distance, right? The distance. What really matters is the distance. What should matter for function? So the question is, what really matters? The shape of the spiral, the shape of the curve, or the angle? It depends on the situation, right? The point is that to have a limit, it means that as soon as you get close, say within one over 100 of an inch, of the origin, the answer is going to be within some small neighborhood of the value that you claim is the limit. It doesn't matter how you approach it; should be within that limit. If it's 1 over 1,000 of an inch, it should be even closer. If it's 1 over a million, it should be even closer, and so on. Right? So the notion of a limit should not rely on the way you approach. It should be uniform with respect to all directions in all points in the neighborhood of the point 0, 0. You see. So in a sense, this argument that I gave you is kind of misleading. It's a very nice argument to disprove the existence of the limit, to show that the limit does not exist. But it is misleading if you try to think in this way about the existence of limits. Okay. So for existence of limits, you have to use a different kind of argument. And now I'm not going to require that on the exams, but I'm going to just to give you an idea of how it works. I'm going to explain it in the following case. Suppose you have a function which is just slightly different from this at first glance. Namely, instead of x squared, I will take x cubed. You see, so what happened? So the problem with this function was that both numerator and denominator had degree 2. So both numerator and denominator, in some sense, are going to 0 at roughly the same speed, but not exactly. It depends on along which direction you go. If you go along this one, it will be 0. Along this one is 1. Along this one, for example, if x is equal to y, you can see it's going to be 1/2. You see, but because the powers are the same, that's why you end up with different answers. What happens now is that I put the numerator. I choose as a numerator x to the third power, and the third power goes to 0 much faster than second power. So that's why this will dominate, and this will kill this guy. So it will become 0. You see, so that's it's hardly killed because they both go to 0. So in some sense, it goes faster to 0, so it doesn't really kill it. But anyway, it depends on your point of view. So how would I show that this actually has a limit? So I claim that this function does have a limit at 0, 0. Namely, the limit is equal to 0. How would I show that? Well, for that I would actually have to estimate the value of this function. I would have to estimate the value of this function when I approach 0. So I will say, let's suppose. So let me explain this as a proof. Suppose that xy belong to the small disk of some radius r. And I purposefully don't want to use delta and epsilon, not because I don't like Greek alphabet, but because I know that people immediately feel violated when I try to talk about epsilon and delta. So I might as well. I think if I use a different letter, you will feel much more comfortable. Or some of you will feel more comfortable. There is a certain, just the way it sounds. Actually, one of the students told me that that it reminds him of going to a dentist's office. Epsilon delta. So let's call it r, and let's look at the disk of radius r. I'm drawing it as a big disk, but actually you should think of it as very small. I just magnified. So this is dr, and I want to look at all the points here, and I want to estimate the value of this function for all points within this disk. So the function, as I explained already many times, is a rule which assigns to each of these points a certain number, which is the value of the function, right? So that's the function f. And I want to estimate the value of the function. What I want to show is that the closer I get here, the closer I'm going to get to the neighborhood of the zero value on this line. So how can I estimate this? Well. What does it mean that it belongs to this? It means that x squared, square root of x squared plus y squared is less than or equal to r, right? That's what it means, because that's the distance. That's how we measure the distance to 0. To belong to a disk of radius r means that for your coordinates x and y, the square root of x squared plus y squared is less than or equal to r. So that means that x squared plus y squared is less than or equal to r squared. But you see, both of these are positive. So if the x squared plus y squared together are less than r squared, this also implies that x squared is less than r squared, right? And so x is actually less than or equal to r. This is actually also clear geometrically, because if you have all points in the disk, you will see that all of them will have the x coordinate less than r, except for the two sort of points which lie on the intersection of the circle with the x-axis. So I know this as soon as my point is in dr, and I also know this, right? So now what I would like to do is I would like to write the following. I would like to write x cubed divided by x squared plus y squared, and I want to measure the absolute value. What matters is the absolute value. When I say it's close to 0, it doesn't have to be positive or negative. It should be very close to 0 on either side. So that's why to estimate it's better to take the absolute value rather than just the value. And so now I want to write it like this. I want to write as x times x squared divided by x squared plus y squared. I've done nothing. I just pulled one x out of this fraction. And then I want to write it as x times x squared divided by x squared plus y squared. right? So now I want to look at this, and clearly this is less than or equal to 1. Because in the numerator I have a squared, but in the denominator I have a squared plus y squared. And this guy is always positive, or 0. So the largest value this can obtain is 1, when y squared is 0. But if y squared is not 0, the numerator will be strictly less than the denominator. So this fraction is less than or equal to 1. And x, as I have just explained, is less than r. Less than or equal to r. So that means that the whole thing is less than or equal to r. So you see, I have been able to effectively estimate the value of this function. I cannot find it for all x and y. I mean, they're all different for different x and y. But I can say for sure that as long as x and y, as long as the point xy is within that disk of radius r, the value is going to be less than r, or less than or equal to, it doesn't matter. So that means that if I make this disk smaller and smaller, in other words, as I take r closer and closer to 0, this value of the function, well, more precisely, the absolute value of the function, will also tend to 0, right? Because for all points within that disk, all points, this value is going to be less than or equal to r. And I have control over r because I can take my points in a smaller and smaller disk. You see, nowhere in this argument am I talking about particular paths approaching 0. I'm talking about the entire disk of radius r. And then I'm squeezing that disk. I'm taking smaller and smaller and smaller. And by being able to use this estimate, I can control the value as a function of the radius. I can say that if I am within the radius 1 inch, the value of the function is going to be less than 1. If I'm within the radius 1 over 100 of an inch, it's going to be less than 100. 1 over a million. In other words, I can get as close as I want to 0 for the value by choosing sufficiently small disk. And that's the argument. That's the proof that the function has a limit, and the limit is equal to 0. And that's what traditionally mathematicians explain in epsilon delta language. But that's all it is. It's just saying that if you take a disk of radius r, then the value of the function for all points within that disk is going to be less than r, or less than something which becomes smaller with r. You see, so that's the argument. Are there any questions about this? So yes. That's right. In general, it will not necessarily be r. It could be, let's suppose I had a different function. For example, I have 2 times x cubed. Then I would prove it's less than 2r. That would still be okay, because I have to get something which will become smaller and smaller as r becomes smaller. Or if I get r to the 1/2, the square root of r, it would also be okay, or r squared. It will not be okay if I just say that it's less than 1, if the whole thing is less than 1. That wouldn't help me. That would just tell me that I get within a certain range, but that range doesn't get smaller as the domain gets smaller. I have to make sure that the range will get smaller as the domain gets smaller. And that's a perfect situation where I didn't have to make any adjustments. It's just I get r on the nose as the estimate, as the largest possible value for this. Okay? Another question? Would that only work? Yeah, well, this is simple. The question is whether this is a general argument. This is not a general case, because in general you're going to have maybe some polynomial in x and y, some additional terms. I have really looked at the simplest case. But in general, the argument is going to be very similar. And if you like, in the book, there are more examples of this type which are analyzed. But as I said, I'm not going to require you to know this. So my point here is just to give you an idea of how this kind of proof works. And I think that even though this is the simplest example, it already illustrates this idea. Okay? Yes? L'Hopital's rule. Well, L'Hopital's rule is really specific to functions in one variable because you have to differentiate, right? So the question was about L'Hopital's rule, which was one of the powerful methods for finding limits for functions in one variable. And so the way it works is that if you have a function which is, say, p of x divided by q of x, and both of these tend to 0, say, and you don't know what the limit is, you can estimate the limit by taking derivatives. Right? So now the situation is different because now we have, this is one variable case. And now we have 2 variables, and in 2 variables we have functions in 2, say, p of xy and q of xy. So let's say I wanted to generalize this. I would have to take some sort of derivative here, right? And this actually brings up the question which we need to study next, which is what kind of derivatives can we do for functions in 2 and 3 variables. Right? So clearly there isn't a single derivative. Because derivative is about the rate of change, right? The rate of change. In a one-dimensional case, there is only one direction in which you can change your variables. You can increase that, you can just go away from x. Apart from the fact that you can change it going left and right, there is essentially only one way to change it. More precisely, there is only one degree of freedom that you can change. You can only change in one direction. But in 2 variables, there are more directions in which you can change and estimate the rate of change, and therefore there are many more derivatives that are possible. So in fact, this is very close to what we discussed up to now. There are so many different ways to approach 0 that we have to be able to take care of all of them, right? So what L'Hopital's rule in 2 dimensions would give us at best is a way to approximate the limit along a particular direction, right? So let's say if I were to take the derivative with respect to the x direction, then I would be estimating what happens when I approach along this line. And if I were to take the derivative with respect to y, I would be estimating along the green line, along the y-axis, right? But neither would give me the full picture. The full picture I can only get, as I have argued, by sort of looking all paths, right? And looking all possible directions. So in that sense, the L'Hopital's rule doesn't help us. Now, sometimes it happens that you can convert this function that you have in 2 variables into a function in 1 variable. One of the exercises, I think it's the last one on homework, is about this, where you can use polar coordinates to realize that the function you have is something like it involves x squared plus y squared. I think it's something like logarithm of x squared, y squared times x squared plus y squared, something like this. So you realize that actually it only looks like it's a function of 2 variables, but actually it's a function in 1 variable, namely this. And then you are back to 1 variable case, and then it becomes a fair game.